I'm going to turn the lights off so that you can see this a little bit better. Is that better, or do you want me to leave the backlights on? Is that good? Okay. All right, so I like to start this lecture with a quote from a mathematician named George Box. Somewhere 30 years ago, and maybe now this is more like 40 years ago, so I'm starting to get old and time's starting to fly by a little bit quicker. So some time ago, and I don't know exactly when, some dude named George Box said, all models are wrong, but some are useful. And I like to use that idea as a starting point for us. Okay? What is it that we're trying to do in this class? We are trying to model a real world thing in the computer. And what are the implications of that? The implications of that are it's a model. It's not going to match perfectly. But hopefully it matches well enough that it's useful to us. And of course that's the whole concept is if we can model it in the computer, we can analyze it in the computer, we can check to see if it's going to break without having to actually build it. Because actually building it is expensive. I mean, can you imagine if they built the Lincoln Bridge and the first time they drove a truck across it broke? Or that, I don't know how many of you walked the bridge that day that you could walk it. Can you imagine if they had the 50,000 people or whatever that walked across that bridge, 100,000, whatever it was, if that day they opened it up, people started walking across, and all of a sudden it like sagged down and touched the water, you know, or something? I mean, you know, obviously that's a little bit humorous, but, you know, I walked across that bridge because I had utmost confidence that our engineering is good enough that we can predict whether it's going to fail before we actually build it. The reality of that is it hasn't always been that way. And the reality of that is today we still screw up sometimes. Today mostly it's an actual mistake as opposed to a misunderstanding of the situation. But there are still cases today where things fail because we didn't understand how it was going to work. We didn't understand the implications of it. Okay? But we didn't think about it in advance. But if we can model the structure that we're interested in the computer, we can analyze it before anything's built, and we can figure out whether it's going to fail, which saves tons of money, saves tons of time to market, because you can go straight to your final project instead of having to iterate through a couple of different prototypes to see what works and what doesn't. Okay? So, what is that?
Lego fire truck.
Okay. Specifically, it's a Lego fire truck, right?
Yeah.
But every single one of you saw a fire truck, right? Anybody see anything other than a fire truck? Okay, but if you look at that carefully, how similar to that is that to a real fire truck? If you asked a computer, is that a fire truck? Would the computer say it's a fire truck? Maybe not. The computer might get obsessed with the fact that it's made out of Legos. And fire trucks aren't really made out of Legos, right? Now, our machine learning, our artificial intelligence algorithms are getting good enough that computers are getting better at recognizing things that aren't, you know, that are representations of what the reality actually is. But for an alien civilization, for a computer vision system, that might not fit the definition of what a fire truck is, because it's made out of Legos and it's probably about 5 inches long, kind of thing. Okay, but we didn't have any trouble at all recognizing that as a fire truck, because it is a model of a fire truck that has similarities to a real fire truck. We can see the ladder, we can see the windshield, we can see the tires, we can see a fire extinguisher on the side. Okay, how close is that fire extinguisher to a real fire extinguisher? Roughly cylindrical and has a little nozzle coming out the top. But if I did a really careful geometric analysis of those, I don't think they're going to be very close. Okay? But my point is, this model is close enough that we recognize it as a fire truck. And that's something I think is fascinating about Legos, is you can build a model of something out of Legos that is close enough that you recognize it as whatever it is. But if you did a side-by-side comparison, there would be huge differences between the two. Okay, so we're going to be doing the same kind of thing with our finite element software. We're going to be constructing a model of it, and as long as we get the fundamental things the same, our models will be very good. Okay, so as long as we have 4 wheels on our fire truck, and as long as we have a ladder, and as long as we have the general geometry pretty close to what it actually is, then we can probably model it in the computer and get some good results. We don't have to match every exact detail in order to get a good model. And so the hard part for you guys, and for me too, quite honestly, is deciding what is critical parts that I have to put in my model and what is extra stuff that I don't really need. For example, I generally don't have to model every single bolt in the structure. That level of detail is not necessary for our structural analysis. Okay, you're going to decide whether this building is going to stand up to, say, 50-mile-an-hour winds. You don't have to model every single bolt and every single joint of the structure of this building. So deciding where to do that is part of the task of things that we're going to learn through this. Okay? All right, here's the catalog description. We're going to emphasize modeling and interpretation of the results. We are going to look at linear static problems for the most part. We'll have a couple other types later on in the semester, but that's most of our emphasis. We're going to use commercial software, and we're going to verify these through theoretical calculations. And I'll just tell you right now, we are going to do theoretical calculations. We're not going to be doing laboratory tests. Okay, so you're going to have to solve a problem in SolidWorks. You're going to have to solve a problem using the hand calculation, and you're going to have to compare those two together. How do we compare two answers? Exactly, thank you. You have to calculate a percent difference. I am so tired of reading reports that say it's pretty close. Generally good agreement. Do not put that in your report. Okay, I want you to say, here is my SolidWorks results, here is my hand calculation, they are 18.3% different. Okay, percent difference is how we compare things. So if it says compare your results, that's a clue, calculate percent difference. So I want to know how close are they to each other. All right, so general statements, if you don't know it already. Finite element analysis, abbreviated as FEA. Okay, and this is sort of like ATM machines. Okay, it's not FEA analysis, right? It's not an ATM machine, it's an ATM. The machine's already in the initials. Okay, so this is FEA, finite element analysis. The A stands for analysis. It's not finite element analysis. Just like it's not an ATM, it's not an automatic teller machine. FEA is a method to calculate be loads on a structure for complex situations. It allows us to do structural calculations for things that we can't pull out our 211 textbook and pull out an equation for. Okay? Now, most of what we're going to be doing in here is stuff that we can pull out our 211 book and do a calculation on, because I want you to do a hand calculation and compare it to the SolidWorks. All right? But the software, once we know how to use it, once we're comfortable, then we can apply the inputs and the constraints correctly. We can define materials and properties correctly. Then we can apply it to problems that we can't find in the textbook. And that's the whole point. The issue is it requires ridiculously large number of calculations. So doing this by hand is not going to happen. Huge numbers of calculations. And the problem is it can be hard to use effectively because there's so many things that you could screw up as you input the stuff that you have to be really critical of your answers. Okay? So in industry, I used to do this for the company that I worked for. We would do the FEA, we'd build the machine, and then before we shipped the machine, we'd go out there with strain gauges and check to make sure that our model represented what we actually built. And the whole point of that was to give us confidence that our models had been correct. Because it's a lot easier to fix things when they're in the shop still than it is to fix things once we've sent something to a customer. Okay? So I am going to harp on that is be skeptical of your output. And honestly, I'd like for you guys to be skeptical of everything. Because there's so much bullshit in this world. Right? Anytime somebody quotes you a number, think about, does that make sense? I'm going to throw Rustin under the bus. He was telling me, we were talking about Thunder. This was the first Thunder he'd been to since he just recently moved here. He goes, yeah, I heard there was 150,000 people down there. No, there was a lot more than that. Maybe 750,000, maybe 1 million people down there. So there was a lot more than 150,000 people down there. Okay? Be skeptical when people start telling you numbers. All right, so the general procedure, and we'll learn more about this. We define geometry with a solid model. You guys have used SolidWorks to do solid models. We define constraints. We tell SolidWorks, how is this thing attached to something? We apply some loads to it, concentrated loads, pressures, whatever, and then we click a button to solve it. SolidWorks creates a mesh. The mesh is a subdivision of the structure into tiny little pieces. And then it does a lot of matrix algebra to solve for the forces on each little tiny piece. And then it puts it all back together again and it outputs us a result. And usually that's in a graphical form, which is a colored graph of the problem. And that's color coded. Usually red means high stressed areas and blues and greens mean low stress areas. Okay? So the general procedure is take a complicated structure, break it down into little tiny simple pieces, do the math on the simple pieces, and then put it all back together again. Okay? So that's in a nutshell. That's what the computer is doing. And by doing it that way, then we can solve complex problems. And this is used in a lot of places other than just structural places too. I think you hear about people doing like weather models that predict the weather. Well, they're taking little pieces of the atmosphere and they're putting in a bunch of constraints and a bunch of inputs, and they're solving it for how it all reacts together. And then it comes up with an output, which is the prediction of whether it's going to rain tomorrow or not. Okay? So it has lots of different applications. We're going to focus on the structural applications because we're mechanical people. All right. Modern FEA, some of the big software packages, of course, are SolidWorks, which is what you guys are familiar with. ANSYS is a specialized FEA program. In my opinion, it's superior to what SolidWorks has, but it's a separate whole thing. I'm not going to teach a whole other package just for the point of teaching how to do FEA. So we'll stick with SolidWorks. ANSYS is used a lot for the big companies that do lots and lots of FEA. Places like aeronautical companies and even the company that I work for, which is not all that terribly big of a company. We use ANSYS to do the high-end analysis work. So you might see that around places. Inventor also has an FEA package for their software. You can do the same thing in Inventor. If any of you were involved in project with delay, you might have done some analysis using Inventor. So of course, as we already talked about, we've had huge increases in computer speed and capacity. The models that we're going to solve will probably solve within seconds. Worst case scenario might be a minute or two. I don't want to harp on stories of back when I used to have to walk to school both ways uphill in the snow kind of thing. But when I was working in industry, it was pretty typical to let models run for days to spit out the numbers. So even just 15 years ago, the advances in the computer speeds and memories and so forth has made this easier and easier to do. But 15 years ago, it might have taken a day to do a model. Now we could probably get it done in a couple of minutes. 30 years ago, it might have taken weeks to get the same number of calculations to. So what that means is we keep getting better and better and more elaborate models is what we're able to do. So 15 years ago, we had to keep the model fairly simple just so that we could get it solved in a reasonable amount of time. We can be lazier now. We can use more elaborate models that have more elaborate geometry because the computer hardware is so much better that we can get it done in a short amount of time. Probably do the same kind of analogy with the way computer graphics in movies has changed. If you go back and look at one particular example I can think of, there's a movie, Air Force One with Harrison Ford, and there's a scene at the end where the airplane crashes into the ocean. And it's, I mean, when I watched the movie the first time, it was kind of like, but it was okay. I didn't really, it didn't really bother me. But the computer graphics are awful. I mean, horrible. And now watching it, it's like, oh my God, I can barely watch this crash because it's so unrealistic. But it's a function of when was that movie produced, and the computer hardware and software wasn't as good as it is today, and you couldn't make it as realistic as it would be if we did that today. Okay, and you can tell it. So the same thing's going on with our software here. I put this on here. This is getting perhaps a little bit dated, but I left it on here anyway. There's not too many traditional drafters around anymore. Okay, almost everybody, modern designers. I don't know if you guys even see the traditional drafter, but when I first started working as an engineer, the company I worked for literally had people still doing hand drawings on boards with pencils. So that would have been going on 20 years ago now. Okay, so about 20 years ago, they were still doing some paper drawings at the company I worked for. So obviously, we're not talking about that type of drafting. Now most everybody is doing CAD work, or almost everybody. And the issue is that the software has gotten so good that those designers can use FEA to start analyzing problems. It's in the software package that you're using, so you can click through and do it. And so my point today with you guys is to teach you enough about the software that you guys can be skeptical that if you're working with a designer that is doing this for you, that you can ask some pointed questions to make sure that the pretty pictures that are coming out are valid. Okay? All right, a little bit of history. Person named Courant described a polynomial solution for a torsion problem, which was the mathematical beginnings of the finite element method. Companies in the 1950s started using the method. The problem was back in that time that Courant actually did this by hand, and it was a relatively simple problem, but the mathematics was cumbersome and it wasn't very efficient. We're going to do some hand calculations. Your first assignment is some hand calculations, and we're going to use probably a 3 by 3 matrix at the most, and you're going to hate me for it because of the amount of calculations that's involved. And we're talking about matrices that are millions of elements, and so doing that by hand is absolutely ridiculous. So the value of this is that once we develop computers that can do all the number crunching for us, then this becomes practical. And that's why it's so useful for us today. So I think we've talked about that already. Increased reliance on virtual prototypes instead of physical prototypes. I think that's kind of obvious. So the concept is we take a structure and we divide it into nodes and elements that connect the nodes together. It looks like my graphic there is overlapping my words. The mathematics of this is a very large system of simultaneous equations. And we solve simultaneous equations with matrices. So the thing we're going to do today is refresh a little memory about matrix manipulations. But the equation that we're going to be solving here is this really simple one that you need to know what this is. Okay? Our equation for all of this is KD equals F. K is a stiffness matrix, D is displacements, is equal to the forces applied. Okay? That is our fundamental relationship. And if you think about that for a second, have you seen that before?
Yeah, springs.
That's a spring equation, isn't it? Okay? So this is totally analogous to springs. We're just doing this on a large scale. And instead of F equals Kx as being just single values for each of those, these are giant matrices. Okay? So our stiffness matrices is a giant matrix of numbers. Our displacement matrix is the displacements of every single possible node. And then our force is a list of all the possible forces that are in the structure. And we're using the computer to solve those matrices for us. Another definition of FEA is piecewise polynomial interpolation. Okay? We're taking a structure, we're dividing it into smaller parts. This gets, some of these concepts are sort of like calculus. Okay? You think back to calculus, you want to find the area under a curve, right? So if what I'm talking about is, and I think you guys have done this before, you have some curve, right? And in calculus, you're given the task of find the area under that curve. Right? You guys done that? You get some nods? Okay, so you've done that. Find the area under the curve. We can use calculus to do that. We can do piecewise algebra to do that too. I could take this and divide this into one area, put a dot there and put a dot there, and this is my area. Right? That's one approximation of the area under that curve. As I piecewise polynomial interpolation of this, I could do multiple dots. I could do several dots on here and do rectangles for each of these dots kind of thing. And hopefully get, well, that one's probably not right, but you know, this kind of thing, right? And as I do that, as my rectangles get smaller and smaller, I'm going to get closer and closer to the true area underneath that curve. right? But as my rectangle gets smaller and smaller, I've got more and more calculations that I have to do. So we're doing the same thing here with our nodes and our elements. We're going to split our structure into elements. Depending on the size of our element, we're going to get closer and closer to the right answer. So ideally, we have an infinite number of elements, and then our model should match our reality perfectly. The problem with that, of course, is that as I go to an infinite number of elements, I need an infinite amount of storage space, and I need an infinitely fast computer to do all those calculations. Okay, so we have to come up with a balance between how many elements are good enough to give me a reasonably good answer, but don't take a ridiculously long time to do it. All right, so finishing up this PowerPoint, back to our statement at the beginning, all models are wrong. I'm going to define 4 types of wrongness: modeling error, discretization error, numerical error, and user error. Modeling error comes from that the finite element analysis is a mathematical model of physical reality. We simplify things, we make assumptions that might be wrong. Okay, I told you earlier we don't typically model the bolts of the structure. Well, that's a simplification, but it's going to introduce error to our results. Particularly if, say, our bolts are the weak link in the thing, and that's what causes the building to fall down. Well, if we didn't include the bolts to begin with, then obviously that's a big problem. Okay? The other thing with modeling error is that the physics of the physical problem might not be completely defined or understood. All right, maybe that goes back to the mountain board issue. The person that did the analysis didn't understand completely what buckling meant versus the way you stand on the mountain board. And so you can't apply the analysis correctly, so that kind of goes into user error too. But if we don't know exactly what's happening physically, then that's going to introduce some errors because we're going to have to make some guesses on what's happening. Okay, those are modeling errors. Discretization error is a thing I talked about where we're dividing our structure into small pieces. As the pieces get smaller and smaller, I get closer and closer to the answer. But I have limits on computer hardware, and I have limits on time that I'm willing to spend on this. And so that falls into discretization error. What we should see is that our error gets smaller and smaller as I get my mesh finer and finer. And we'll talk through the semester about techniques for refining the mesh to get the improved results. Numerical error comes from rounding and truncation of numbers in equations. It can also come from bugs in the software. This is unlikely to happen, but it's out there. I put in Poisson's ratio equals 0.5. Theoretically, Poisson's ratio of 0.5 means that we have an incompressible substance. Some rubbers have that characteristic. And the problem with that is that in the math and the equations, if you put in a Poisson's ratio of 0.5, you will cause problems for the software. Numerical instability, divide by 0 type of errors. All right, so if you're dealing with a rubber that has a very high Poisson's ratio, you put in like 0.49 instead of 0.5. So just be aware of that. That's like a special case. But years ago, when people were first developing the software, it actually crashed the program. Most modern software has things in there to check for those kinds of simple errors. But just be aware of that you're going to create numerical instability. That means you're going to get runtime errors. Sometimes you'll get messages pops up says SolidWorks is unable to solve this problem. That could be a possible source. And then user errors. We can click the calculate button with zero understanding of what's going on. You might get lucky and you might get a good result, but also obviously more likely to not get a very good result. We can also make small mistakes. You forget to put a force in there, you forget to put a constraint in there, you put a constraint in the wrong direction, all of those kinds of things that will throw off the answers. And so we reduce those, and I will harp on it. You know, education is what we're trying to do so that you reduce the likelihood that those types of things happen. Okay? All right, I think that's all I had in that slide. Any questions about that?